Around 2 years back, I had a session in with the Jadavpur University, and apart from that, I haven't been much acquainted to the Kolkata University or the Eastern universities. Though I had taken sessions with them, Ramanujan, a number of times, and there we have a number of participants from these two universities also. Anyway, so I am take actually in this session we are discussing the concepts related to principal component that will eventually leads to exploratory factor analysis. And one more thing, we all are in the academics. It is just the matter of chance that I am on the other side. Even then, we all are in the academics. So whenever some issue is there, you can always indicate and you can always ask also. And don't worry about the PPT and the case. I will share with Mr. Daya so that they would be ultimately shared with you. One more thing that I have mentioned earlier also to Dr. Shikha, I am using the dual screen. So if sometimes if there is some issue, some compatibility issue with the sharing part, kindly do indicate. So now I'm sharing the screen. Is it there?
Yes, sir. Yes, it's visible.
Yes, sir.
Okay. Right. So before starting the concept, let us take a very simple example. Though this is not the main case that we are dealing, I am taking a very simple example. So to establish what we are going to do. Suppose we are thinking of taking admission to some university or some institution, or we are thinking of getting admitted to any ward of us or any person who is known to us, uh, or someone has asked about how that particular university or institution is. Suppose we have examined certain features or certain variables um, uh, like the qualification of the faculty members of that university, the research publications, courses offered, the revision of the courses, and whether these courses are useful for different domains, both theoretically as well as the application part. And we also have examined some more features like whether how what is the condition of classrooms there, how good hostel is there, whether that university has some playground, and what about the mess and canteen facility, and whether that campus is having Wi-Fi facility or not. So we have examined so many features. Okay. And on the basis of this, we are going to evaluate that university or institution, so to decide whether we are going to that university or not. Now, if we observe these variables or these features, right, what impression we get means what we are examining here. We are actually examining something that is known as academic content or academic quality of that institution. And if we observe these features or these variables, what actually we are examining, something related to infrastructure content. Isn't it? Right? So now we see what actually we are going to do. So these variables or the features are visible to all of us. These are the variables that are visible or that are open to us, and through these variables we are trying to find out something that is beneath the surface or that is known as underlying dimensions. So we can say that academic content is an underlying dimensions beneath these five variables or these five features. In the same way, this infrastructure can also be known as the underlying dimension that are beneath these variables. Okay. So actually what we are examining here, we are actually examining two concepts. The first one is we are exploring the underlying dimensions that are inherent in the data or that is beneath the surface behind this data. And here we are identifying two underlying dimensions, one representing academic content, other representing infrastructure. And the simultaneously here what we are going to do, originally we have 10 variables, right? And these 10 variables can be represented by or can be reduced to two dimensions, dimension 1 and 2. So this is the objective for which we are going to study this concept. Means simultaneously we are examining what are the underlying dimensions beneath the surface or behind the data, and how these variables can be reduced to some manageable things. And the related concept is technically known as dimensionality reduction. So dimensionality is just the second name of these underlying dimensions or the factors or the things that is there. And here we are studying two concepts which are related. One is the principal component analysis, and very much related to this is exploratory factor analysis. So so this is the objective of studying this chapter or this unit. So any question? Yes, participants, any question if you like to ask? Oh, okay. So,
No, sir.
okay, thank you. Thank you.
No,
Thank
sir.
you. So, this is a concept that we are going to study here. Now, let us discuss the statistics behind that. Here, we cannot identify means whether this is affecting the second variable or the second variable is affecting the first variable. So we can say that the direction of the relationship is actually both way, right? So means the direction of the relationship is both way, not the unidirectional relationship. So this type of technique is known as interdependence technique. Unlike regression analysis, logistic regression, or other techniques like discriminant analysis, so this is known as interdependence relationship. So here we are examining interdependence relationship among these features. Okay. And since there is no since all these variables are uh, unlabeled one, means we can at most label them like x1, x2, x3, x4, x5, like x6 and x7. There is no y variable. So if we say about the machine learning part, this is known as unsupervised learning. So this is the unsupervised learning part because it does not have label data. So it does not have label data, no label data. And further going with the statistic, how we can identify that these features are related, like qualification, right? What statistical things would be there? So actually we are using the concept of correlation among these features, right? Means if data-wise they are correlated, then we can place them in a single dimension. And if they are correlated among themselves, so that is the correlation behind themselves. So this is the concept that we are going to use. So all these things are there in the PPT. So what is the objective? Here we examine actually the data structure, means what is behind the data. We examine the data structure which is there in the data or interrelationship of the variable. This I have mentioned. This is interdependence technique to define underlying structure among the variables with minimum loss of information that we will discuss later on. This we have discussed unsupervised learning. Now, when we started the discussion, we don't know how many underlying dimensions are there. So we have identified these two underlying dimensions through the empirical discussion. So we don't know forehand. So there is no prior constraint. Take what the data gives you. So this is a part of empirical analysis. Why we are discussing this concept? Because there is a related but very different concept that comes under structure equation modeling, that is known as confirmatory factor analysis. So in that case, we go from theory to the data, right? Or we go from construct to the variables or indicators. And here, what we are doing, we are moving from variables to the dimension. So this is opposite. So in that case, we actually establish the theory, we prove the theory, and here we are examining what is there in the data through the empirical analysis. Okay, so and these are the two objectives that we have discussed. The first one is the data summarization, that is the exploring underlying dimension. And the second one is the data reduction, identifying representative variables much smaller in number for the subsequent multivariate analysis. You people must be familiar with the concept of multicolority, very common with the cross-sectional research. So multicolority is a big problem whenever we consider the cross-sectional data. So this can be used uh, as a way to reduce the multicolority also. So any question up to this part, or should we move forward? If someone has some problem, so that person can text. Otherwise, I am taking the case. So before that, I am just establishing the concept. So this is actually the research design part. The first thing is the variable selection. Obviously, it works through a statistical analysis. It works through a software. So and statistical analysis recognizes only the numbers. So if we select some irrelevant variables, obviously, um, in some extreme cases, they may show some type of relationship. So it is very important that relevant variables means that are belongs to a particular situation also having correlation should be taken up. Otherwise, garbage in is garbage out. Now, the technique that we are going to discuss is actually required that our data is measurable in nature. Means either we are going with the either we are going with the interval scale or we are going with the ratio scale only. Means at present, the technique that we are going to study, that is a PCA, we are not going to use nominal scale or the ordinal scale. Right? And this is a large sample technique. What is the thumb rule? That the minimum requirement is for every variable, there should be 5 cases and preferably 20 cases. Suppose we are considering 9 variables in our case. So we require that there must be 45 cases, and it would be good that we will be having 180 cases or 180 sample. Remember, this is a thumb rule, but do remember this is a large sample technique. So before moving forward, let me share the case. Kindly read this case, or should I share this case? Just a moment. That is possible, but probably I can't share anything. Okay, no issue. Right? I will share this later on. Just read this case. And this case is actually written from the perspective of Procter and Gamble. It is related to a very common product all of us are familiar with. It is related to the baby diapers. Actually, it started with the trade war between the two FMCG joints. One is the Procter and Gamble that manufactures Pampers, and other is Kimberly Clark, uh, that produces Huggies. Initially, Procter and Gamble was the market leader. Later on, Kimberly Clark has taken over. And but in the recent time, because of the different strategies, Procter and Gamble is again leading the market. So obviously, for this, Procter and Gamble wants that everything should be as per the need of the consumer. Right? So that's why they are going with type of a market research survey related to the consumers. Here, remember here the actual consumer is the toddlers, which are too young to give any appropriate answer. So the person that is involved is their mothers, who is actually the decision maker, or who can be termed as the customer who is taking the decision related to the baby diaper. Okay. So here the important part starts. Procter and Gamble marketing department wanted to formulate new approaches to the construction and marketing of its diaper, that is Pampers. So they have surveyed 300 mothers of the infant who purchase um, the diaper. They have given a randomly selected brand of the diaper, and they are asked to rate the diaper on the 9 attributes, as well as to give their overall preferences. This is on the extended 7-point Likert scale. So for the time being, we are not taking the overall rating. We are considering only these 9 diaper attributes, which will be the part of our case. So these are the 9 diaper attributes. They are in front of you. The first one is the count per box. The second one is the price. The third one is the value, and so on. And the last one is tapping. And mothers are being asked to rate these diapers on a scale of 1 to 7, where 1 means they are not liking, they are not preferring, and 7 means they are liking. So this is the case that we are going to use for this discussion. So any question up to this point? Okay. So just a moment. Okay. So now I am sharing the case and we will be discussing. So this is a data set that we are going to use. Here we are not using this variable, that is the preference, which is actually the dependent variable. For the time being, we are not using. This will be the part of some other multivariate analysis. So these are the 9 diaper attributes that we have discussed, starting from count to tapping, which actually represent the diaper attributes. So we are expecting that there is some dimensionality behind these 9 variables. Okay. The first I am explaining how we run. Then we again come to the concept of this factor analysis. So as all of us who have used the SPSS, they know that all the analytical tools are available under the drop menu of Analyze. So we click Analyze, then we go to the dimension reduction. So this is the dimension reduction. And here it is technically known as factor. And in the factor analysis, we are actually employing the principal component analysis. Okay. So here I am selecting these 9 diaper attributes, starting from count, going up to the tapping, and transferring them to this box, which is the relevant part. And we are also instructing some command buttons also, like the descriptive. Some options are checked beforehand, but we are also including some others like univariate descriptive. Since correlation is the basis, so we are clicking the coefficients, and we are also clicking the KMO and Bartlett test. Okay, and simultaneously we are using this reproduce correlation. When we discuss the output, then all these things would be clear why we have chosen this option. So for the time being, you can have some patience. We will be revisiting all these concepts once we have the output, and we are discussing the results in light of the analysis of this uh, case. Then we go to the extraction. Here we have different type of techniques, and at present, since PCA is the topic that we have taken, so we are selecting principal component. But remember, there are other techniques also, other methods also. But why we are taking a PCA? Because this is the most common one, and in all the normal situation, it is supposed to be the better one as compared to other. Here we are analyzing correlation. Correlation is actually the standardized value of the covariance only. Here we also include scree plot, and at present the criteria for extraction is, we are using just this criteria. There are other criteria also that we will be discussing during the concept discussion. So at present we are using, it is based upon the criteria for the extraction of principal component is based upon eigenvalue, and the criteria is eigenvalue greater than 1. There are other criteria also, but for the time being, we are taking up this only. Then we come to the rotation, though we may not include rotation because this is actually the part of the factor analysis, but just for the interpretation purpose, I am using varimax rotation. So once I have selected varimax rotation, so display rotated solution also got highlighted. Then we come to the score part. Score part is again not that much required for the discussion of PC or factor analysis. It is the thing when we use, say, for some other multivariate technique. So just to demonstrate that, I am taking up save as variable. Remember, when we save anything on the SPSS, that will be saved on the data sheet. So at present, the data sheet last variable is tapping, but here we are also including save as variable. So the dimensions of the principal component that are created would be there on the data sheet also. Okay, and then we press OK. So this is the output that we are going to discuss. Okay. Remember, there are some very important questions that will be there in your mind that we will be discussing during the due course. So don't worry. Everything that I have taken and everything that I have just selected would be there once we discuss. And I have used a screenshot also, so that will be useful. That means this PPT, when I share the PPT, all these things are there in the screenshot, so you won't face any problem. Okay. So here, now again, I am taking up my second screen. So before moving forward, let me explain what do we mean by principal component. Then we move forward. Okay. So just a moment. Okay. Participant whiteboard is there?
Yes, sir.
Yes, sir.
Okay. Okay. So let me explain what do we actually mean by principal component. Suppose we have a data set having two variables only, that is x1 and x2, right? So at present we have only two dimension, x1 and x2, and here the cases are being expressed. These cases are being expressed because this is a bivariate data. Now, if we consider the dimension which is covering the highest variation, so this is just a moment. So this is the direction of maximum variation in the data. Now, why we are taking up this term, that is the variation. Actually, this variation represent the information that is inherent in the data. That's why in all the statistical analysis, we interpret or we explain that analysis through some type of variation analysis only. So whenever we say this is a direction of maximum variation, means the maximum information is there in this direction. And this direction of maximum variation is actually known as principal component. Let me put this as principal component 1. This is the main principal component. Now, if we consider the other dimension, so this is the other dimension. This is known as PC2. So this is the direction of the remaining variation, or the direction of second highest variation. Since there are only two variables, so there will be only two principal components, that is PC1 and the PC2. And remember, these principal components are at 90 degree. This is PC1 and PC2. So these principal components are actually known as orthogonal principal component. They are known as orthogonal principal component. Now, related to the mathematical part, how these principal component are being calculated, right? Here we actually consider the characteristic equation. You may ignore this part also. The characteristic, suppose this is a matrix, A is n cross n matrix, right? So we solve this determinant, that is A minus lambda I, where this is the determinant, right? This is A is the matrix for which we find out the principal component or the eigenvalues. So this is A. This is the determinant. This is the matrix. I is the identity matrix. And this lambda is the n eigenvalues. And we solve this for the different lambda, right? And then, so these lambdas are known as eigenvalues. And when we solve this matrix, A minus lambda I into x equals to 0, that is Ax is equal to lambda x. So now here x is known as eigenvector. And when we multiply our data set with this eigenvector, we get principal component. So this is the mathematical part which is behind that. If you don't want to follow that, you can very well ignore that, because this is a part of the statistics people. Anyway, so these two are the dimensions, right, that we are covering. So here we actually have two variables, that is x1 and x2. Now suppose and we have two principal component also. So we have two principal component, that is PC1 and PC2, right? Suppose we want to reduce data. So if we take only PC1, right? So we are reducing two variables into one principal component, and thereby sacrificing a small amount of variation that is being covered by PC2. So here we are reducing the data, and what we are actually giving up, what we are sacrificing the remaining information that is being covered by PC2. Right. In the same way, if instead of these two dimensions, if we consider the three dimension, suppose they are x1, x2, x3, there are three variables. So now it will have the three principal component also, that is PC1, PC2, and the third one is at the 90 degree, that is PC3. Okay. So here we have three variables like x1, x2, x3. So there are three principal components, that is PC1, PC2, and PC3. Okay. Now we want to reduce. if we take only one PC1 that covers the maximum of the variation, this is the best reduction. But here we are sacrificing high amount of information or high amount of the variation also. So instead of this, if we take two principal component, that is PC1, and the second one, which is covering the maximum of variation, that is PC2. So thereby we are compromising on the reduction, and but we are also capturing the higher amount of the variation or higher amount of the information. So this is the concept on which the principal component works. I know this is a bit mathematical. Even then, we should know the what is there in the black box. That's why I have explained. So any question related to this concept, so kindly ask. This mathematical part of the eigenvalue and the eigenvector can be ignored. Yes. So anything you like to ask? Or should we move forward?
Move forward, sir.
Okay.
Move
So,
forward.
okay. So if this is okay, right. So now we are moving forward. So these are the screenshot that I have mentioned. So now the first thing that we want to discuss that is related to determining appropriateness of the data, means whether this data is capable enough to be applied for the principal component or the factor analysis. The first thing is, means we examine whether there is dimensionality or not. What we are going to do, whether there is dimensionality or not. So how they can be examined. First, we discuss the conceptual issue. Means conceptually there should be some underlying structure. Okay. So what is the conceptual issue of our case? Since we are considering the baby diaper attributes, so it is expected that they represent the same concept, the same thing, the same requirement, same expectation. So there must be some underlying structure. Fine. Now, this is the conceptual issue. Now we will be discussing how we can identify through statistics or what are the statistical issue involved. So here we try to quantify the degree of intercorrelation that we have just discussed. So how this degree of intercorrelation can be justified? Obviously, I have discussed that it is based upon the correlation analysis. Means there should be high correlation among variables. Okay, so I am sharing the output. So now that can also be discussed there. Okay, now if we see for this case, it is expected that for some mother, if count per box is important, means how many diapers are there in the box. So for that mother, price might also be important. For some mother, if price is not important, then obviously count per box may not be important. If some mother is very much interested that diaper should provide absolute absorbency to her kid, so that mother must be very much interested in it should also provide the comfort also. So when we follow these variables or the attribute, it appears that some variables are some variables may be correlated with each other. So in order to confirm that, we examine this correlation matrix. Okay. Now there is one more table before this correlation matrix, and let us discuss what is the objective of this table. Here, mean and standard deviation is just the descriptive measures that we use for some other purpose. But the last column is very important because this is the analysis which represent whether these are the valid observation, they represent the volume of the missing observation. Since this case has been made for the demonstration purpose, so it is not having any missing observation. But in any real life situation, in any real life survey, there may be a number of missing observations also. So it is just to tell us what is the valid sample size on which analysis is being run. Right? Now, related to the statistical issue, so to identify whether we are using the appropriate tool or not, or whether our data is appropriate for principal component analysis or not, we are examining the correlation matrix. This is a symmetric matrix. We are having similar variables on the row side and similar variables on the column side. And these coefficients represent the correlation. So obviously, all the diagonal elements will be 1. Why they will be 1? Because here they represent the correlation coefficient of one variable with the other, right? So that's why they are the same one. Is that okay? So we examine actually the non-diagonal elements. So now here 0.864. This is the, so here there are two matrices. Actually, there are two parts of this matrices. If we consider the diagonal, so on the above part is known as upper triangular matrix, and below the diagonal part is known as lower triangular matrix. Since this is a symmetric matrix, so upper triangular and lower triangular are similar. So either we interpret upper triangular or we interpret the lower triangular. So let us discuss the upper triangular only. So 0.864 is the correlation coefficient between count per box and price chart. So this is a high correlation. 0.730 is a high value. It is the correlation coefficient between price charge and the value. Similarly, 0.942 is a high value. 0.731, that is a high value. 0.894, that is a high value. So we are observing that a number of coefficients in the correlation matrix are showing high value. So we can say that a number of non-diagonal correlation coefficients are showing high value. So is that okay? Is that okay? Or any question? Okay.
Sir, explain once more, sir.
Okay. So we discussed the correlation matrix. So this is the diagonal, this is the symmetric matrix. We have similar variables on the row side and similar variables are on the, just a moment. Just a moment. We have similar variables on the row side and similar variables are on the column side. So all the diagonal elements are 1 because the correlation coefficient of variable with itself will always be 1 only. So ignore that. Now here, since this is a symmetric matrix, so the coefficients that are on the upper triangular are exactly same on the lower triangular. So that is known as upper triangular matrix or the lower triangular matrix. So we are actually considering only one part, either upper or triangular, they are the same thing. So here we look for whether there are some high non-diagonal values or not that represent the correlation coefficient between different variables. Like this value 0.864, which is actually the correlation coefficient between count per box and price chart. That is a high value, right? In the same way, 0.730, a high value. 0.894, a high value. 0.942, a high value. 0.753, a high value. So number of terms, 0.894, a high value. So number of non-diagonal coefficients are showing high value, which represents that these variables are highly correlated. Is that okay?
Yes, sir. Okay.
Okay. Now I am considering the another concept. Let me take a bit of statistic so to explain that. So just a moment. Actually, we have two types of correlation coefficients. Yes. We have two types of correlation coefficient. Suppose we have three variables, x1, x2, x3. So the first one is known as bivariate correlation that we have just discussed, right? Means this is the correlation coefficient between 1 and 2, correlation coefficient between 1 and 3, correlation coefficient between 2 and 3. This is the bivariate correlation. right? Suppose these variables x1, x2, x3 are highly correlated. So when we calculate the bivariate correlation coefficient between x1 and x2, it will show a high value because the third variable, that is x3, which is not been shown here, it is been included in the bivariate correlation also. So because of the third variable, they will show high correlation also. But if we consider other type of correlation, that is known as partial correlation, which is R12.3, which means correlation coefficient between x1 and x2 controlling the effect of x3. Now suppose x3 is highly correlated with x1 and x3 is highly correlated with x2. So when we calculate bivariate correlation, so the impact of x3 on x1 and x2 are included. But when we consider the partial correlation coefficient, so here x3 is being made constant. Since x3 is being made constant, so we are considering only the correlation coefficient between x1 and x2. So in this case, this partial correlation coefficient may show the low value, right? So if there is dimensionality, we will be getting high bivariate correlation and low partial correlation coefficient. And this difference is being examined by KMO measure. This difference is being examined by KMO measure. So KMO measure represent this difference that we will be discussing later on. So is that okay? This concept related to bivariate correlation and partial correlation? Or anything you like to ask?
Okay, sir.
Sir, the partial coefficient is always lower than the bivariate.
No. It can be equal to that also. But if there is high dimensionality, suppose x3 is highly correlated with x1 and x2. So in that case, the impact of x3 would be included in bivariate correlation. So obviously the value would be high. But when we remove the impact of x3, the partial correlation coefficient would be low. But if x3 is not highly correlated with x1 and x2, so it doesn't matter whether x3 is included or not. So in that case, there won't be much difference between bivariate correlation and the partial correlation. Is that okay? Is that okay, Mr. Chaudhary? Okay, right. Now, since we have discussed the, so these two concepts we are simultaneously taking up where we discuss this concept. So here, what happened? Correlation matrix. It shows high diagonal coefficient. It is there. And the second concept is high correlation coefficient but low partial correlation coefficient. It shows the presence of the dimensionality. Now we will be discussing this concept in a big detail. I have just shown you the correlation matrix, but the question arises whether we should take up that correlation coefficient as a high value or not. So for that, let us discuss this Bartlett test of sphericity. So for that, I am explaining the correlation matrix. Suppose I am taking the three variables only, that is x1, x2, and x3. We are considering a short form of the correlation matrix. Here, all diagonal elements would be 1 because they represent the correlation coefficient between the same features. And if this is the situation, mean all the diagonal elements would be 0. So this type of matrix is known as identity matrix. Right? Now, if our correlation matrix is an identity matrix, it simply shows that all the non-diagonal elements are 0. Means there is 0 correlation among the variables. So that represents that data is not appropriate for the factor analysis. So this is being done by the Bartlett test of sphericity, where the null hypothesis is correlation matrix is an identity matrix. Okay. And if we reject this matrix, Okay. Reject H naught means this is not an identity matrix. Then we can say that there is substantial correlation. And for the rejection, we know if the p-value or the significance is less than 0.05, then we say that H naught is being rejected. So now I am showing you the output. Just a moment. Output is there, class? So here we are discussing this Bartlett test. Here the p-value is, as you check, the p-value is 0.000, which is less than 0.05 in this case. So we reject H naught, means we are rejecting that this is an identity matrix. Okay. So here, as per the output, here output is showing that the p-value is 0.000, which is less than 0.05. So we reject H naught. So we reject H naught means we are rejecting that correlation matrix is an identity matrix. We are rejecting means this is not an identity matrix. There is substantial correlation among variables. So we can say that our data is appropriate for PCA. Is that okay? Or any question you like to ask? Obviously, if p-value is greater than 0.05, if p-value is greater than 0.05, we are not rejecting H naught, and we are not rejecting H naught means uh, um, means we can say that correlation matrix is an identity matrix. So there is zero correlation, there is insignificant correlation. So our data is not appropriate for the factor analysis. But it is not the case here. So we can say that our data is appropriate for the principal component analysis or the factor analysis. Is that okay? Means the
Okay,
concept.
sir.
Okay. Now, we are discussing the second concept that I have just explained, that if bivariate correlation coefficient are high, but partial correlation coefficient are low. So for that, we examine the second feature that is known as KMO measure of sample adequacy. Right? It compares the magnitude of the observed correlation coefficient with that of the partial correlation coefficient. So in case of dimensionality, observed correlation coefficient would be high and partial correlation coefficient would be low. Right? So actually the KMO measure is the difference between observed or bivariate correlation and partial correlation. So if bivariate is high, partial is low. So obviously the value of KMO measure would be high. If there is not much of the difference, then KMO value would be low. So if we get high KMO value, right? So it represents that data is appropriate for the principal component analysis. So the value of KMO lies in between 0 and 1, and high value indicate the appropriateness of the data for the principal component. And here, as you check, the KMO measure is 0.803, which is very near to 1. So we can say that our data is appropriate for the principal component. Right? So here we have discussed the first part related to the appropriateness of the data, and we examine the data as a whole is appropriate for the principal component analysis. Is that okay? Is that clear?
Okay, sir. Clear, clear.
Okay, thank you. So now we have discussed only the overall data. Now we are considering the individual variables also. Like, it is possible that overall data may be appropriate, but it is not necessary that all the variables are appropriate for the, just a moment, all the variables are appropriate for the principal component. Right? So now I am explaining one more concept. Now let me explain how this concept works. Actually, we considered if there is high correlation among variables, right? So if there are high correlation among variables, so they are move in the whenever one variable got changed. So there is a simultaneous movement of the variable on the movement of one of the variable. So if there is high correlation among variables, we say that these variables share high common variance. And this high common variance is being extracted by principal component, right? So if high common variance is there, it shows that variables share high common variance, right? Means this is known as variance extracted. So if variance extracted is high, it shows that variables are sharing high common variance. Further, it shows that the variables are highly correlated. And this variance extracted is technically known as communality. This variance extracted is technically known as communality. So let me introduce the definition here also, the formal definition. Communality is total amount of the variance a variable share with other variables in principal component. This variance is being extracted in principal component that I have just discussed. Right? So if high communality is there, it shows high common variance, and high common variance means they are highly correlated. Means that variable would be highly correlated with other variables. It shows that the particular variable is showing high dimensionality, and that variable is appropriate for the principal component. So let me show you the output. So this is the communality table. As you see, this is the communality table. We are employing principal component analysis. So principal component analysis starts with the complete of the variation. So this is the 100% of variation. So initial communalities are always 1 for the principal component. And here it is showing the communality. Extraction is written here. So from count per box, 86.2% of the variation is being extracted. It means count per box is having a common variance of 86%, which is a high value. This is a high value. It means that a variable is participating in the principal component analysis. So here we go with the thumb value of 0.5, means all those communality that are above 0.5 are supposed to be appropriate for the principal component analysis, and they will be included in the analysis. If a particular variable show low communality, that will be eliminated, and we will recalculate, we will redo this analysis. So this is the principal component. As you can see here, all the variables are showing high communality. Means we will be taking up all the variables for the further discussion. Remember, this case is being made for the teaching purpose. So that's why it is showing high communality. It may not be there for the different studies when you go with your part. So here, this definition is written here. This is a variable specific measure of intercorrelation. It decides appropriateness of variables for principal component. So high commonality is decided, right? Otherwise, the value is 0.50. This is the thumb rule. Otherwise, we drop variable and recalculate till the acceptable level is being obtained. Is that okay, class? So actually we have discussed the two concepts. One is overall appropriateness, and after that we have discussed the appropriateness of, okay. So I am explaining communality again. Just a moment. So here, if there is high correlation among variables, since there are high correlation among variables, so they will show simultaneous movement. So we can say technically that these variables share high common variance. And this high common variance is being extracted by the principal component. And this is known as variance extracted, which is technically known as communality. So if high communality is there, it shows high common variance among variables, which further shows that they are highly correlated. So that simply tells us that the particular variable is appropriate for the principal component analysis. So Miss Ananya, is it okay? Okay. So finally, I will be sharing these slides so you won't face any problem. So high communality is desired. And here I have used the definition, total amount of the variance a variable share with other variables. So up to this part, we are discussing related to appropriateness of data for the principal component analysis. This is the first part. Now in the second part, we will discuss how many principal components are extracted. So now I am discussing that part, how many principal components are extracted. So for this discussion, I am taking up this table, that is a total variance explained. It has three parts: initial eigenvalues, next is the extraction sum of square loading, and after that rotation sum of square. Here we are discussing only the initial eigenvalue. So let me explain what does eigenvalue means. So this is a definition. Eigenvalue is also known as latent root. It is the amount of the variance accounted by or extracted by a principal component. Okay, this is the column sum of square loading of a principal component that I will be showing you. And sum of eigenvalue is equal to number of variables included in the principal component. Why this is so? Because in PCA, every variable has initial contribution of 100% of the information. There is no data loss. Means all the initial all the initial communalities would be 1. So that's why here sum of eigenvalue is equal to sum of number of variables that are included in the principal component. Now let me show you the output. Here, this is the initial eigenvalue. Remember, we have 9 variables. So there are 9 dimensions. These are the 9 components. And these are the eigenvalue. So the first principal component, as you see here, there is a defined decreasing trend of the eigenvalue. Because the first component or the first variable extract the maximum of the variation. The second variable extract the maximum of the remaining variation. Third variable extract the maximum of the remaining variation. So there is a defined decreasing sequence as you checked, right? And if you sum all these eigenvalues, that would be exactly equals to 9, because there are 9 variables or the 9 principal components, and everyone is contributing the 1 only. So these are 9. And here eigenvalues are being converted into the percentage of the variation by the formula lambda I divided by sum of lambda into 100%. Means 4.973 divided by 9 into 100. What we get? 55%. 1.534 divided by 9 into 100%. What we get? We get 17%, and so on. So these are the percentage of the variation which is being calculated from the eigenvalue. And this is a cumulative sum. 55.254 plus 17, we get 72. 72 plus 11, we get 83. So the sum is 100%. So hopefully this part of the total variance explained is clear to all of you related to initial eigenvalue. Is it clear to all of you?
Yes, sir. Yes, sir.
Okay, right. Now, kindly have a screenshot of this because I will be using, just a moment. Have a screenshot of this because I will be using these values. Okay, right. Done? Just a moment. Now let us discuss what is there in the table. Now we have 9 variables. Now remember, for the principal component analysis, it has two objectives. Number one, reduction. That is a data reduction. We want to reduce our variables, we want to reduce our data. And the second thing is, it should try to capture maximum of variation or information. That is, there should be minimum loss of variation or minimum loss of the information. Remember these two things. Now, here we have variables and here we have dimensions. Initially, we have 9 variables and the best reduction would be, just a moment. Here we have the dimension. So 9 variables, suppose, has been reduced to 1 dimension only. So this is the best reduction, isn't it? But it captures only 55% of the variation. So 45% of the information, 45% of the variation is being sacrificed. Right? So now we consider the second case. Now we compromise on the reduction. So 9 variable has been reduced to 2 dimension. So there is a compromise on the reduction. But as from the table, now it is capturing 72% of the variation. So now sacrifice of the variation, sacrifice of the information is just 28%. We consider the further case, right? Suppose 9 variables are being reduced into the 3 dimension. So there is further compromise on reduction. But now we are capturing 84% of the variation, 83.959. So thereby we are sacrificing just 16% of the variation. If we further go, 9 variable has been reduced to the 4 dimensions, so thereby we are capturing 90% of the variation. So one thing becomes better, obviously the other things become worse. So that's why we have taken that concept, that is the eigenvalue over 1. Right? So let me show you that table also, so that we may, just a moment. Okay. Now here Here only three factors are being, principal components are being extracted because they are showing eigenvalue over 1. Now, what is the logic of taking eigenvalue over 1? That I have just explained on the whiteboard. Okay. So if we take only one factor, or only one dimension, this is the best reduction, but it will capture only 55% of the variation. There is a sacrifice of 45%. If we take two principal components, right? So there is a compromise on the reduction, but now 72% of the variation has been captured. Now we further go for the further compromise on the reduction. If we take three factors, then obviously there is a compromise on the reduction, but now principal components capturing 84% of the variation. So this is somewhat better as compared to the other one. Again, I always say that principal component analysis and factor analysis is as much art as science. So it depends much upon the researcher how many principal components should be taken. Here at present, I am taking the criteria that is taking eigenvalue over 1. So only three factors are being extracted, which is in the second part of the table. So any question up to this? Or is it clear to all of you?
Yes, sir.
Okay, right. Now remember, this is not the only criteria. Yes. Here we are discussing deciding about number of factors or number of principal components. The first one is the eigenvalue criteria. Here we have discussed. Here we go with the eigenvalue over 1 criteria. Right? There can be a priori criteria. Suppose we know forehand that there should be 4 dimensions. If we know forehand, then we put in the start that 4 dimensions would be extracted. The next one is the percentage of the variation criteria. If that is the criteria, suppose we want 70% of the variation only, right? Remember, if we want only 70% of the variation only, then we recommend how many factors? We recommend number of factors as 2, right? Then we recommend number of principal component as 2. Suppose we have a criteria of 80%. Then we recommend that number of principal component should be 3. If we have a criteria of 90%, then number of principal component of factor should be 4. Right? So obviously much depend upon the researcher how much variation is being required. Normally, the default value is, or the thumb value is, it should have at least 60% of the variation. Anyway, we are using the other criteria. So this criteria is clear? Hello?
Yes, sir. Clear.
Okay. Now we are discussing the script plot criteria. So this is the script plot. Script plot is being made using the eigenvalues. So here we have 9 components. These are the 9 components. And here we have the eigenvalue. The first eigenvalue is very high. This is 4.973. So it is showing a very high value. Then we have a big slope and so on. Now this part is known as scree, where there is less of the slope. So if we compare this with our shape of our arm. So when we have our arm, so the initial part up to the elbow, there is high slope, and right up to the elbow, there is high slope, and after the elbow, the slope got decreased. So we consider the elbow position. So elbow position represents us the appropriate number of factors that should be taken. But issue with this observation is, for some person, elbow is here. So if we go with this elbow, that person would be recommending number of eigenvalues as a number of principal components as 2. For some person, elbow can be at this position, that is 4. Right? So that person would be recommended that number of principal components should be 4. right? So obviously different criteria may give the different results. But what is the objective of using the elbow criteria? Because after the elbow, only principal components would increase, but there won't be that much substantial increase in the percentage of the variation captured. So this is the script plot criteria. So, right. Let us discuss one more criteria, then I will take the question if there are some. The last one is the split half reliability criteria. In this criteria, we divide our data into two parts and run principal component analysis on the separately, and by comparing the results, we decide what should be the appropriate number of principal component. So remember, here we have discussed number of, and there are 5 criteria that we have discussed. So that I have told, there is not a single criteria that is absolute. There are different criteria may give different results in the different situation, and they may be good in different situation also. So that's why we are discussing all these criteria, because remember I have told in the start that this is as much as art as the science. So much depends upon the researcher, what his or her requirement or the criteria is. Okay, so these are the different criteria. At present, we are using only eigenvalue criteria. Okay, is that okay? Any question?
अच्छा but WhatsApp kala
Hello,
mail le pathiye
Mr. Mandal, any
हाँ sir
question?
okay no sir okay sir
Okay. Other participant, is that okay? Because indeed, though we are going with the first criteria only, but indeed as a researcher, we should know what are the different criteria, and in some different situation, other criteria may give some better results. Okay. So now we have discussion up to the 2 part has been completed. Number 1, the appropriateness of the data. Number 2, how many principal components should be taken. Right? So here we are going with the 3 principal components. Now the next question arises, what name we should give to this principal component. So that would be useful for some practical aspect. So here I am explaining the concept of the loading. Right? So here I have discussed these 2 things, that is the communality and the eigenvalue. Okay. Now I'm explaining this part that is related to the factor loading. What do we mean by factor loading? Now suppose we have 3 principal components. Suppose this is F1, this is F2, this is F3. And here we have variables like X1, X2, X3, X4, and so on. Right? So these factor loadings actually represent the correlation coefficient between this variable X1 and the factor F1. Suppose this value is 0.90. It shows that there is a correlation coefficient of 0.90 between X1 and F1. In the same way, suppose this value is 0.20. Suppose this value is 0.15. So it shows the correlation coefficient of 0.15 between X1 and F3. So these are known as factor loading. Now, if this is the situation, then you can simply say that this X1 is having very high correlation coefficient with F1, and other correlation coefficient are much relatively low. So we will be placing this X1 in this factor F1. Right? So this is a situation. Now I take some other situation. Suppose in here we are having this correlation coefficient 0.60. Here we have correlation coefficient 0.55. Here we have correlation coefficient of 0.56. Right. Now mathematically X2 is showing the highest correlation with F1. But there is not much of the difference between this correlation coefficient. So there is always a doubt whether x2 should be placed with f1, x2 should be placed with f2, x2 should be placed with x3. So this situation is known as cross loading. Okay. Now I will be showing you the definition also. Okay. Just a moment. Factor loading is the correlation of the variable and the factor. This I have discussed. Related to the cross loading, a variable has two or more principal component loading exceeding a threshold value. Okay. Right. And this is the definition of the factor loading that I have just mentioned. This is the correlation coefficient of a variable and the principal component. Is this concept, the further concept I will be explaining later on. So these two things are clear related to the factor loading. Right? Let me show you the table also. This is the component matrix, right? And where we are discussing this factor loading means the correlation coefficient of count per box with the first principal component is 0.761. Correlation coefficient of the count per box with the second principal component is 0.485. Correlation coefficient of count per box with principal component 3 is 0.219. Right? So here if we say the highest value tells us that count per box is having highest correlation with principal component 1. So it should be put with the principal component 1 or PC1. Is all these discussions are clear to all of you? Is it clear? Right? Why we are going to discuss? Because we want to identify what name should be given to this principal component. Remember, the principal component are beneath the surface. They are the underlying dimensions. So we try to identify their profile or their possible name through the variables that belongs to them. Okay. Now all of us should observe this component matrix. Now here we are placing count per box in the principal component 1. Now if we come to the second variable, price chart, though it is showing highest correlation here, but 0.524 is very close to the high value. In the same way, if we go to the next, unisex versus separate sex, though 0.744 is a very high value, but minus 0.64 is very close by. Minus sign simply indicate the direction is opposite. And the style also showing the cases of cross-loading. So in this component matrix, there are sufficient examples of the cross-loading. Further, if we try to place these variables, we are observing that all the variables are showing very high correlation with principal component 1 only. Right? So if we go with this table, we can say that all the variables should be placed in the principal component. Remember, this is not very strange. Why this is not very strange? If we square all these values, 0.761 square plus 0.750 square plus 0.611 square plus 0.744 square, right? And we sum them, it will be exactly equals to the first eigenvalue, that is 4.973. In the same manner, if we square all the coefficients of the second principal component and add them, so that will be exactly equals to 1.534. In the same way, if we square all the coefficients of this principal component 3 of the component matrix and sum them, that would be exactly equals to 1.050, right? Since the first principal component is capturing the highest percentage of the variation, showing the highest eigenvalue, so it is very much expected forehand that all the values are showing high correlation coefficient with the first factor only. Let me show you this. Right. Yes, this is the thing that I am discussing here, that squared factor loading. It tells us the percentage of the variation in the variable explained by the dimension, right? So it is equals to the eigenvalue. Okay, so here again definition is there. It is the column sum of square loading of a principal component. Sum of, right? So this is the part that I have just discussed. It is the column sum of the square loading of the principal component. So what is the issue with this discussion related to the unrotated component matrix? Unrotated factor solution achieves the objective of data reduction only, but have cross loading, and might be possible that all the variables are highly loaded on the first factor only. So it should not be used for the um, interpretation purpose. So that's why we won't be interpreting uh, this component matrix. We will be interpreting the other one. So conceptually, if there is some question, kindly ask. Anything you like to ask, or if there is some confusion why we are not, right? Though I shouldn't take the component matrix, but I am taking up just to establish the concept that is known as rotation of the dimensions. Any question up to this point? Yes, participants. Any question? Hello.
Sir, what if the correlations are negative? In that case,
The negative correlation simply tells us that it is in the opposite direction. Let me show you through the uh, diagram. Just a moment. Okay. Now, this is variable x1 and x2. As we know, these are the positive dimensions, right? But this also represent the x1. It is the negative part. Okay. In the same way, this is the negative part of x2. Now, suppose this is the direction of the principal component. So this part is positive, but here also the dimension is there. This is also PC1. So this part is positive, this part is negative. Is that okay? So negative correlation means it is related to the negative part. Means the scale is opposite. Like if someone asks some positive thing, we give answer in the positive word. If someone asks a negative thing, we give answer in the negative sense also. So they represent only, negative part only represent that the question is negatively worded, and if we want the positive value, the question should be positively worded, right? So my correlation coefficient is the correlation coefficient. Plus and minus sign simply indicate the direction only. Plus sign, they are moving in the same direction or the direct relationship. Minus sign, they are moving in the opposite direction or the inverse relationship. Is that okay? Okay. Any other question, or should we move forward? Okay. So now, since the this unrotated component matrix or the component matrix cannot give us the interpretation of the data, so we have to do something else. So now I am explaining that concept. Just a moment. Now we are discussing the concept that is known as factor rotation. So up to this part, we are actually discussing the principal component. Now, if we include the rotations also, right, this complete part becomes exploratory factor analysis. So actually, they are just the two sides of the coin, they represent the same thing. Means up to this part, we are discussing the principal component. Now we are also considering the rotations of the dimension. Let us take an example. Though this rotation is actually the matrix rotation. So I am not discussing the mathematical part. I am just giving you a broad idea what does it achieve. Just a moment. Now we have these two dimensions. This is PC1, this is PC2. Here also we will have PC1 and here also we have PC2, plus and minus sign. And suppose we have 5 variables. This is variable 1, this is variable 3, this is variable 5. Here we have variable 2 and here we have variable 5. Now if we observe the variable 1, it is being loaded on PC1 as well as it is being loaded on PC2. In the same way, if we go with the variable 2, it is being loaded on PC1, it is being loaded on PC2 also. So they are showing high amount of cross-loading. Now, we rotate these dimensions mathematically, right? So now they are being rotated and this is the new position. Means it has been rotated here. Right? So this PC1, this is PC1, this is PC2. In the same way, other dimensions are being also rotated, maintaining the 90 degree. So now this PC2 has been rotated to PC2 and this is PC2. Now we consider this rotation part. Now here we see that all these variables V1, V3 and V4 are highly loaded to PC1 and relatively very small loaded to PC2. So now there is no cross loading. V1, V3 and V4 can be put in PC1. In the same way, V2 and V5 are having very high loading on PC2 and very low loading on the other principal component, that is PC1. Now they are far apart. So we can put V2 and V5 as a part of PC2. So this is known as factor rotation. This is actually the explanation of Varimax rotation. And in the Varimax notation, we are maintaining the axis at 90 degree. So this is also an orthogonal rotation. Okay, let me introduce the formal definition also. This is the factor rotation. Process of manipulating, adjusting the factor axis to achieve the meaningful or pragmatic factor solution. And this is beyond principal component. Orthogonal factor rotation, a factor rotation in which factors are extracted so their axes are maintained at 90 degree. Now, what is the benefit of putting them at 90 degree? They will show uncorrelated or they will be independent of each other. And this is the Varimax rotation, orthogonal rotation that maximizes the sum of variance of the required loading. Here, now we are discussing this rotated component matrix. So, is it clear? If that is so, I am showing you the table. Is it clear? Hello?
Yes, sir.
Okay, right. So now, just a moment. So instead of this, now we are discussing rotated component matrix. You people can have a screenshot of this. Remember, so far up to this point, only principal component is being mentioned. But here, along with the principal component, Varimax rotation has also been mentioned. And this is through 4 iterations of the matrix multiplication. That means the mathematical part that can be ignored. So kindly have a screenshot of this, though I am placing this on my table. Okay. Now, this is the solution. This is the rotated component matrix. Okay. Now we are discussing this part. This Excel sheet is visible to all of you?
Yes, sir.
Okay. Now, we check whether there is cross-loading or not. In the count per box, here, highest correlation is being shown, but other values are quite low. So there is no cross-loading. Now, if we go with the price chart, here highest value is being shown, but other values are 0.193 and 0.243. Other values are relatively much low, so there is no cross-loading. In the same way with the value also, right? So here, count per box is showing highest correlation or highest factor loading with the component 2. So it is being placed in the principal component 2 or factor 2. This price chart is showing substantially high correlation with the principal component 2. So it is being placed in the principal component 2. In the same way, value has been placed in the principal component 2. Is it okay? Is it okay, class?
Okay, sir.
Okay. Now we come to the next part, that is a unisex versus separate sex. Here it is showing the highest value. So we color them. Right. In the same way, style also, it is showing the high value here, and other values are quite low. Now we come to the absorbency. Here we are getting the highest factor loading. So we put some other color. Right. In the same way, leakage is also showing the highest value with principal component 1. And here it is also showing the highest value, and tapping is also showing the highest value with principal component 1 or factor 1. Okay. So now you see there is no cross loading and there is a division of variables among the 3 factors. Right. So we will be interpreting rotated component matrix so that we have some idea about the possible names that can be given to these factors. So is it okay? So I have just copied this from this output. This is a rotated component matrix. Means we are ignoring component matrix. Why we are ignoring? Because they achieve just the reduction part, but it is not interpretable because of 2 reasons. Number 1, there is cross loading. Number 2, all variables are being loaded to first factor only. So it is not that much useful for our purpose. Right? So we are interpreting rotated component matrix. Is that okay? Or any question?
Sir, I have a doubt.
Yes, please ask.
Sir, if
And
the
speak a bit louder, please. Miss Amreen.
hello.
Hello.
Yes, sir. Sir, my question is, if the variables show high correlations for different factors, so which factor should we consider?
Yes. If they show high correlation with different factors, that is the case of cross-loading, right? So that is not a good solution. Means either there are 2 reasons. Number 1, that variable must have low communality. Remember, we have discussed the communality. So that variable must have low communality. And we have ignored the communality part and we have included in the factors, right? So because of that, it is showing high values with different factors, right? Because it is creating a confusion part. And even if that is not the part, this a variable showing high value with more than one um, dimension is a typical example of this cross-loading that I have explained. That variable has two or more principal component loadings exceeding a threshold value. So it means a variable cannot load it to a single factor. So this is not a good case. So we should avoid that solution. So that's why we normally interpret mm, the rotated component part. But you even in the rotated component part, like here, even in the rotated component part, if variable is having high correlation with more than one factors. So we should check first whether communality is high or low. Even if the communality is high, it means the variable cannot be loaded to a single factor, right? So this is the drawback of exploratory factor analysis. That's why in order to confirm, we recommend confirmatory factor analysis through structured equation modeling. So is it okay, Ms. Amreen?
Sir, my question was, sir, will you show the Excel sheet?
Yes. So the question Ananya has written, should we drop that variable? Yes, if that variable is showing high communality, low communality, that variable should be dropped. Then only we run the remaining part of the principal component analysis. Yes. Here we don't have um, uh, the cross loading. This value is very high, 0.224, 0.251 is showing very low value. So normally in the rotated component matrix, if we have selected the appropriate variables by taking the conceptual part as well as by considering the communality part, we won't face that much problem. And even if that problem is there, definitely we should drop that variable. Yes, Ms. Amreen?
Sir, according to rotated component matrix, here variables have high correlations with different factors. So which factors should we consider?
One moment. Look, these are the variable. Look only for the count per box, right? Count per box is having high correlation with, is having 0.224 correlation with factor 1 or principal component 1, 0.865 with component 2, and 0.253 with the principal component 3. So if we have to place, actually we have to place the variables. Components of factors are unknown. They are the underlying dimensions, right? So to which component this variable count per box would be placed? Obviously to 2. Is that okay? Now, don't look this table vertically. Look this table horizontally.
Okay. Sir, if I want to run a regression here, then which factor should I consider?
Wait. That part would be there. That part I would cover later on, right? I will be taking that part definitely. So for that part, I have created the factor score on the SPSS data sheet also. That is there. Is that okay up to this part?
Yes, sir.
Okay. Now, there must be some, or this is a very common product. So let us place. In principal component 1, what are the variables that are there? These are the variables. Let me copy and paste this. Okay. Right. In principal component in factor 2 or principal component 2, we have these variables. Okay. And then we have factor 3. For principal component 3, we have these two variables. Okay. My question is, means the first factor represents the combined feeling of absorbency, leakage, comfort, and tapping. Like the four variables that I have initially used in order to introduce the concept, we put a broad name of academic content to that dimension. So this dimension actually represents the attribute of absorbency, leakage, comfort, and tapping. So can we suggest any name to this principal component of factor? Yes, anyone? Can we suggest any name to this dimension? Remember, the product is the baby diaper, right? And the responses are given by the mothers of those babies. So what name can be put to this factor? Yes, anyone? Hello? Can we put this name as the utility?
Diaper quality.
Quality, yes, quality is there, but I suppose utility is a better word. If you ask some mother whether it is a utility product or not, the mother would respond that it should provide absorbency, it should check leakage, it should provide comfort. Is that okay? So you can put either quality or utility. Is that okay, class?
Yes, sir.
Right.
Utility, sir.
Yes, sir.
Right. And in the same way, if we want to put some name, this is count per box, price charge, and the value. So it is related to something related to money or the value. So in marketing, this term is very popular, that is value for money. Right? Is that okay? Which covers price part as well as the value part also. So can we put this name as the value for money?
Yes.
Okay, sir.
Okay. Right. In the same way that this part can be written as the design or the fashion part, because they represent the design or the fashion part of the diaper. Right? Is that okay? Right?
Okay.
Obviously, the name will be different and the domain, and it requires the domain knowledge. So obviously, the people who belong to this domain of the consumer behavior or the marketing, they may suggest some other names also. Right? Anyway, it depends upon the domain. Suppose the problem is related to economics. So the people of the economics may suggest some better name. Anyway, so this is as per the domain knowledge, we put this name, utility, value for money, and the design or the fashion. Is that okay? So these are the three possible names that are there. Right? Fine?
Okay, sir.
Okay. Now, we have discussed this part also. That is related to rotated component part. Right? Here, everything is there. Remember, these orthogonal factors are correlated with each other. Right? Remember this concept. Now the question arises, what should we discuss about the data reduction? Right? Remember, originally we have 9 variables. And these 9 variables has been reduced to 3 dimensions. Now we go with the further multivariate analysis, like as Amreen has asked. Suppose we want to use them for uh, linear regression. So what are these 3 possible dimensions? One thing is, just a moment. One thing is, since here utility dimension is actually consists of these 4 features. So we can take only one variables instead of these 3 because they are correlated, right? So we have absorbency, we have leakage, we have comfort or tapping for the first dimension. So instead of all 4, we can take only one. Suppose we take here leakage. We have taken the leakage. So instead of these 4, absorbency, leakage, comfort, tapping, we have taken leakage. Why we have taken leakage? Because it is showing the highest factor loading, highest loading, right? And in the second part, there are 3 variables, count per box, price charge, and value, and we have to take one only. So here we can take the highest one, that is the price charge. So here, instead of all 3, we can take price charge. In the last part, we can take style only. Is that okay? This method is known as surrogate variable or the salient variable. Means instead of all, we take a representative variable. So the case that I have just explained now by taking only one variable is the example of surrogate variable or the salient variable. Right? Just a moment. Right? So if for this, we take the data only for the leakage, right? So these are the three variables only. And if we include these three variables for running the uh, linear regression part or multiple linear regression part, they won't show much of the multicolority. Now, issue is whether we should go with this method of surrogate variable or salient variable or not. What are the possible objections? There's a data loss. We have collected data on the 4 and we are using only one feature. So there is a data loss. So this is not a good method. Is that okay, class? So those surrogate variable or salient variable is a way to reduce the data, but not a good part because number one, there is a data loss. Number two, as we see here, there is not much difference between leakage and comfort. And we are going with only mathematics and we are selecting the leakage. So anyone can object why we are not taking the second value, which is very close to. Right? So there are these two other objections. Right? Is that okay? So surrogate variable is not a good case. So how this solution can be improved? So if we don't want to make the data loss, what we can take? We can take the average of these values: absorbency, leakage, comfort, and tapping. Right? So that in the same way, for the second factor, we can take average of these values. And for the third case, we can take the average of these two values. Right? And this method is known as summated scales. Right? What we do? In the salient variable, we take only one representative value. Only one representative variable. And what are the objections? There is a heavy data loss. So not much recommended. In the summated score, what we take? We take average of all constituent variable. Simple average. We take mean or arithmetic mean of all. Is that okay? So here we don't have data loss. Right? But what is the objection? Someone may object that now you are putting equal importance to absorbency, leakage, comfort, and tapping. But here, leakage is showing high relationship and tapping is showing low relationship, right? And you are putting equal importance to all of them. So you are ignoring the factor loading part, means you are ignoring the weighted component, weighted part. So here we have the objection. What is the objection here? We ignore the relative importance of variables. Okay, so we have the last method, that is the factor score. So instead of simple average, we take the weighted mean of all constituent variables. Okay, so we take the weighted means there is no data loss. All variables are being included. Further, there is justified importance. Right? So we take these weights, like this is the highest weight for the absorbency, this is the highest weight for the leak. Right? So we take these weights in order to calculate the factor score. And after that, they have been standardized. And in this way, we obtain the factor scores. So now I am showing you that. Then I will be taking the questions again. Now just let me change the screen. Now these are, right now SPSS sheet is there. Now these are the factor score that I have discussed. Now we can rename them. Like the first factor can be written as utility. The second factor, just a moment. Second factor is value for money. The third factor is design or fashion. We save this. These are the score. Now the question that was asked by Amri, if we want to run the regression analysis, right? So you can extend this case to this. In the first part, in this preference is a dependent variable. In the first part, include these variables, so that it will show severe multicolority. But instead of that, if we use the factors or the principal component instead of the variables, it won't show the multicolority. Right? So here we include them in the linear regression and we run the regression analysis. So we will be having a solution which is not showing multicolority. Right? So hopefully I have answered that was asked. Right? So this is all about. Now I am ready to take questions. And I will be sharing everything with you. So don't worry about